Hello and good afternoon, everyone.
Good afternoon.
Glad to see everybody here.
Nico.
I see that a number of you have already completed the flip video for our peer teaching for today. I'm eager to start looking at those. I don't want to start posting them and evaluating them until everybody's got theirs in. So if you haven't done it yet, please make sure that it's done by the end of today would be great. I realize there's a time differential, but these are really, really key in me evaluating how well you're getting stuff and to be able to give you kind of one-on-one advice and mentorship on what you're learning in the course. And so it's super, super helpful. Like I said, it looks like I've got from 1, 2, 3, 3 folks so far. So we need to do just a little bit more on that. I'm sorry. We got 1, 2, 3, 4, 5. Okay, so we're going pretty good on that. Let's see. Glory is the only one that I don't see yet. So hopefully, she'll get hers in on justifying science. I'll start watching them today and you'll start getting feedback probably. You'll see feedback by tomorrow. Okay, so let's hop right into it. If there's no other questions, I'm going to hop right into today's lecture. The PowerPoint is posted on Moodle. Shepard and Glory, we're still working on getting your IDs worked out so you have access to Moodle. So I'm still also uploading all the videos and the materials onto YouTube so you can watch them that way. But okay, we shall get started. If folks don't mind turning on their cams, I appreciate that you do desire. If everybody else would as well. I hate teaching to an empty room. It makes me feel all alone, and we don't want that. Okay, so let me go ahead and talk about what we're going to talk about today, which is not that, it's this. Hold on, let me resize that. And we'll zoom up to here. So what we're going to talk about today is alternate data sources and what I call paleo proxies. Hopefully we'll get to the paleo proxies, but we have a lot on alternate data sources as well. And in terms of objectives of this section of the course, I'm going to want you to be able to describe multiple independent data sets that confirm, what we are seeing in the surface thermometer temperature record. You should be able to identify which time periods are associated with each data set. Not all of them stretch as far back as our thermometer data. Some go much even further. You should also be familiar with the measurements and conclusions of each of the data sets and be able to cite them. You'll have to be able to talk about what a paleo proxy is, how the measurements are made, what exactly they're measuring, and how we now interpret that in terms of temperature or other information. You should also be able to describe what the early Earth looked like and how the climate has changed since then. And with that, be able to explain these periodic temperature changes, such as glaciation and interglacial events that are associated with these different time periods. It's really important to read chapter 2 of the textbook. There is a link that I've sent out on information on the textbook, etc. If you haven't gotten it yet, I really strongly suggest that you do. I believe it was Naya Mungo, somebody in here had a PDF and knew how to go about properly getting the textbook. So please do. I tried to select this textbook because I think it's well written and it's very up to date and modern, and I think the perspective it comes from is going to be really useful in the rest of the course and the program. So what we talked about last time was the surface thermometer record. Okay, this goes back, we've got good worldwide coverage all the way back to the 1850s. And we talked in lectures 1 and 2 about temperature anomalies and how by using temperature anomalies, we actually don't need as many thermometers around the world. We could actually probably measure world fluctuations with just 100 well-placed thermometers. There's several more than there's several thousands in the surface thermometer record. And the coverage is pretty good. And we've been recording data for a long time. So we talked about that. You should be really familiar with that. The other thing you should be familiar with, if you look at this graph, you should know this number. So the temperature anomaly that we're seeing now in 2023 is about 1.1 degrees Celsius higher relative to the 1850s, so the mid to late 19th century. And that's a really important number to know because that's going to give us scale to understand what's going on now and what kind of scale we're talking about in the future. Should also know, I think I pointed out in the last lecture, that that is an average temperature for the entire globe, right? And we saw from some of the fancy pictures that we have that temperature difference is not uniform. So there's warmer regions and colder regions. We know the northern hemisphere heats warmer than the southern hemisphere because there's more land in the northern hemisphere. And so that means that although we see a 1.1 degrees Celsius global average change, it can actually be very different depending on where you're looking at it. So the colder regions of the southern hemisphere are being averaged with the warmer regions of the northern hemisphere. So where most people live, we're actually seeing much more than a 1.1 Celsius degree temperature change. So that's our surface thermometer record. And as all good scientists do, we like to have a lot of different ways to confirm or to validate the experiments and the data that we're seeing, okay? And we'd like to have a bunch of different ways. And we talked about that a lot in chapter 1 and the first 2 videos on the scientific method, that you can have a lot more confidence in a conclusion when it's supported from multiple data sets, multiple independent data sets, a variety of different researchers, et cetera. That gives us great confidence in any kind of scientific conclusion. And so, so our best data set is the surface thermometer record. Okay, that's the main one that we'll be using. But there's other data sets out there. Some of them are going to directly measure temperature. Other data sets are going to measure things that we would predict would change with temperature. So like the satellite record, for example, that's going to mostly directly measure temperature, not like a thermometer does, and we'll go through that. But then we're also going to look, one other data set we're going to look at is the ice record. Now, that isn't a thermometer record, right? The ice record is something that we might expect to change depending on what the temperature of that region is, right? If it gets warmer, we would expect ice to melt. And so if we make all these conclusions that the world is indeed warming, there should be other things that support that. So we should see ice melting, for example. The bulk ocean. So now we have a surface thermometer record, but what about the deep ocean? Okay, if the surface is warming, one might also predict that the deep ocean would warm as well. And so we'll take a look at that. And then if all this land ice is melting, that's going to flow off land into the sea. We would also expect there to be changes in sea level. And so there's a sea level data record that goes back quite extensively that we'll talk about as well. So the idea here is we're trying to get multiple independent data sets to kind of confirm our conclusions about global warming. And if they don't, it has to make us ask the question, well, what's going on? Is our conclusion incorrect? Okay, so the first one we'll start with that's used a lot is the satellite record. So satellite data has been available since about 1979. And this is very different. It's not using thermometers. So this is a different data set than the surface thermometer record. It uses a different modality. So these satellites, what they're doing is measuring either infrared radiation coming from the Earth or microwave radiation coming from atmospheric oxygen. There's two main different ways that these satellites can measure temperature. We know that there's a direct correlation between how hot something is and how much infrared light some will give off, how much infrared radiation. If you've ever seen an infrared camera and someone walking around, you can see they're kind of glowing red. That's showing that they're warmer. And these satellites work in a similar fashion. An important thing to mention about this is that every measurement is going to have some kind of errors, right? We talked about in the surface thermometer record how you might get trends and errors produced by the urban heat island effect in urbanization, how that could lead to a trend. Talked about that last time. That's not the case with the satellite record. You wouldn't have an effect, the heat island effect, on thermometers with the satellite record, right? It has different kinds of errors and things that can change the measurements, like orbital drift, for example, is something that can complicate measurements with the satellite record. If you move a little bit further away, your measurements of the incident infrared radiation or microwave radiation will be lessened. Okay, so it's important to keep that in mind, that the errors that you would see with the thermometer record are going to be different kind of errors than you see with the satellite record. And that helps us because if there's a set of errors that are consistent, okay, like in the thermometer record, that would give us a different kind of a conclusion, those errors will be taken out with the satellite record. It'll have its own errors, which would point in a different direction. And if we use a lot of different data sets with different error sources, then all of those should cancel each other out, and we should be able to come to a trend if there is one. Okay, so let's focus first on satellites using infrared measurement. I've put on here a list of a variety of high-tech satellites that have been used since the 1970s, and some of these are more modern, that have been using infrared to measure the temperature of the planet and various portions of the planet. The first one is the Advanced Very High Resolution Radiometer, or the AVHRR. And so this is a satellite. It's an instrument that's carried on a satellite, part of the NOAA, or of the NOAA series of polar orbiting platforms. NOAA usually has, it's the National Oceanic and Atmospheric Association and Administration. And NOAA usually has at least 2 polar orbiting satellites at all times since 1981. So they've been measuring data since that period. And this gives you kind of a picture of what you can see in terms of that data from NOAA. I'll go ahead and expand it out so you can see what kind of the temperature variation is that it's seeing over the planet here. This is from 1985 to 1997. Not showing any conclusions here yet, just giving you an idea of what kind of instruments are being used to get these satellite measurements. And usually these instruments are one component of a satellite that may have many components. It may also have several different weather-related or climate-related instruments on the same satellite, each gathering data in a different fashion. In the case of the AVHRR, this is doing high resolution in the infrared. There's also the long track scanning radiometer, or the ASTER. This is one of the European Space Agency's devices that's on the Envisat satellite. This was launched in 2002. It's very precise. It can measure temperatures with a precision of about 0.3 degrees Celsius all the way from space. So that's pretty cool. And in terms of the stability of the measurements, again, this is related to the type of air that you see in satellites as you get this orbital drift. When the orbit starts to drift, if it starts to get a little bit further away, it will change your temperature readings because there's less radiation getting to the sensors. And so the stability of this has been measured to be about, it'll vary about 0.1 degrees Celsius for every 10 years. This one can also measure sea surface temperature, which is a really good thing. And here's some data from the ASTER. So this is what some of the data looks like. And so down here in blue, this is the data that was measured, the yearly data. So we're going from January to December. Here's temperature. So we're going from January to December. In the 1970s, those are shown as independent tracks on here in this darker blue color. In the 1980s, we go to a lighter blue color, and you see a number of tracks for that decade. You see tracks for in the 2000s. And one of the things you might be noticing is that these tracks are getting higher and higher and higher. So in the 2010s, we have this kind of lighter red color. 2020s is this darker red. And for 2023, the current year that we're in, these are the measurements up until July of 2023. What kind of conclusions do you draw from this satellite data, just taking a look at it? Now notice we're not doing an anomaly here at the moment. What do you ascertain from this graph?
I see a trend of temperature increases from the 70s up until this point. And it's a gradual trend. Each year is seeming, well, each decade is seeming as though the temperature is increasing. At least from the sea surface. It's a gradual increase in temperature.
Okay, and so sea surface temperatures getting warmer. That's fairly apropos. Right now, we actually have to shut down Claflin at 3 o'clock today because of Hurricane Idalia has just made landfall in Florida, which is not too far from us. Now, originally, when they were predicting the hurricane, they had originally thought that it would probably hit Florida as a Category 1 or Category 2 hurricane. And then as it moved further, the predictions raised to a Category 3. It actually ended up hitting as a Category 4. And the reason why it keeps increasing its intensity is it travels over warmer ocean water, especially shallower water as you get closer to the continent. The energy of the hurricane starts to pick up dramatically. And so we went from a lower category of hurricane to a Category 4 right now that's hitting landfall because it intensified so quickly. And one of the things they're saying right now, although it's not peer reviewed, it's just what they're saying on the news at the moment, is it's one of the fastest intensifications that people have seen. And indeed, it's the worst category hurricane to hit that region of Florida in 150 years. So this high temperature of the sea surface has a dramatic impact on our climate and our weather. And if you look at the 2023 track, what do you notice about that?
The 2023 one resembles.
Yeah, so it's significantly higher than the rest of the tracks. Now, this could be an aberration, right? We don't know yet. We have to collect the surface thermometer data and a variety of other data sets, but at least according to Aster, this is really showing a significant jump in sea surface temperatures beyond what we would have expected by, this normal decadal trend that's going up from 20 degrees to about 20.6 degrees. Might not seem like a lot, but it does have an effect, especially on these hurricanes. And it's consistent. Okay. So besides using infrared, satellites can also use what's called microwave sounding. Okay. Molecular oxygen in the atmosphere will, based on the vibrations and the excitations that it normally gets in the atmosphere, will release radiation, usually in the microwave spectrum. Remember, the electromagnetic spectrum is very, very large. Just a small portion is visible light. The shorter wavelengths would be infrared. The shorter wavelengths would be ultraviolet. The longer wavelengths would be infrared. Even shorter, though, than the ultraviolet are these microwaves, and those can be sensed by some of these satellite devices, okay? And what they allow it to do is measure temperature in different levels of the atmosphere, okay? Because depending on the pressure of the oxygen, the concentration of the oxygen molecules present in a region, that will have an effect on what frequency microwaves are sent out. And so right over in this graph I'm showing here on the y-axis is the height in kilometers above the ground, okay? So this is going from 0 all the way up to 30 kilometers. And you can see at different kilometers, okay, this right here is the frequencies that you would see and the intensities of those frequencies. So certain frequencies have a much greater intensity depending on what level you are above the earth. And so by looking at those specific frequencies, we know if we look at this particular frequency, we're actually looking at excitations of atoms of oxygen that are in around between 15 to 20 kilometers above the earth. If we see excitations in this frequency range, that's probably from about 10 kilometers up. And then there are other frequency ranges, which can give us land versus ocean. And so we can actually tell the height. We can measure at different heights based on which frequency we want to look at. And so this is where it's important to kind of go over what you may already know about the layers of Earth's atmosphere. There's different layers to it. And so the topmost, first you've got space, and then the first layer of atmosphere, the outermost layer of the atmosphere, is what we call exospheres. That's where satellites will be up located, spaceships go out there, but not much else. Beneath that, we have the thermosphere. If you ever see the aurora borealis, that's happening up in the thermosphere. The mesosphere is where there's enough oxygen and enough gases that when a meteor is passing um, uh, towards the Earth, that's where it will start to catch fire and burn up as it's hitting the mesosphere. That's between 40 to 90 kilometers above the Earth. Now, as you get lower, we now get into the stratosphere. This is where people send weather balloons. This is anywhere between 11 to 50 kilometers above the Earth. And if we go back to our microwave sounding, you can see this is where we're getting one of our first big peaks, is between 15 and 20 kilometers above the Earth. And so between 15 and 20 kilometers, that would be in the stratosphere. Okay, so we're able with our microwave sounding satellites to be able to measure oxygen excitations in the stratosphere. And then beneath the stratosphere is what we call the troposphere. That's anywhere from zero, from ground level, all the way up to about 12 kilometers. Okay, that's what we experience, what we live and breathe in. We're in the troposphere. That's where planes fly, hot air balloons go, and if you go up on a mountain, you're still in the troposphere. You haven't quite entered the stratosphere yet. And if we look back at our microwave sounding graph, you can see that in that region, there's a number of different excitations, specifically these that will tell us data specific to the troposphere. So what does this data show us? So let's go ahead and look at some of the results from some of these microwave sounding instruments. And so here's a measurement of the lower stratosphere. And so what they're trying to show here in this picture is the trend over a decade. So it's Celsius per decade. So this is an anomaly temperature, right? And so what it looks like here, so if you're in the red, that would mean warming. If you're towards the blue, that would mean cooling. So what conclusion would you draw from this between 1980 and 2016 about the stratosphere? This is the lower stratosphere. So this is based on data around here. Remember this excitation over here between 15 and 20. Our stratosphere is between 11 and 50. So this is going to be the lower stratosphere. And this is kind of our, this is the data that we're getting. So what would you conclude about the temperature of the stratosphere? What's happening to it? Desire, you want to throw in your thoughts? You're on mute. Go ahead.
I'm not really sure because this the globe, allow me to call it, it's more blue on the southern hemisphere than the northern. So in the south part, it could depict that it's cooler, but that doesn't mean it's the same with the northern part. The north, it's mostly white, which is not really cool but warm.
Yeah, so white is, there's not much of a temperature change, right? So white is the zero over here. I'll go ahead and blow this up a little bit so we can see this better. Okay, so let's get out of the way. So zero is the whitish here, but for most of the region in the northern hemisphere and even a lot of the southern hemisphere, what do you mostly see? Are we warming? Glory? Yeah. So this is clearly showing cooling, correct? Yeah. So we're not saying we're not warming. What are we saying isn't warming? The stratosphere, the lower stratosphere, okay? Remember, that's a really specific region of our atmosphere, right over here, okay? Now let's move down a little bit. Remember with our with our microwave sounding, we can go into the troposphere, right? Our troposphere is, you know, anywhere below the stratosphere, which is this main signal. So we have a number of different signals that can tell us about the troposphere. And so here's microwave sounding of the troposphere. I see a couple shocked faces. Now, wait a second. This said this is getting cold. This is getting warm. Why? How can that be? What? Wait, I don't understand. This is confusing. Doesn't gas mix? Can anybody explain what's going on here?
I personally think, like I still remember actually in my geography class before, I think it was in elementary or something like that, we always have this phrase that the higher you go, the cooler it becomes. So I guess this is the effect that happened here. On the Earth's surface, inclusive of the oceans, it's warmer. Whereas as you go up, it becomes cool.
Okay. If that was all that was going on, so it gets cooler as you go up, right? But what we're being shown here isn't the temperature of the stratosphere relative to the troposphere or relative to the Earth. This is measurements of the stratosphere relative to how it was a decade before, right? So wouldn't you expect, if the Earth is warming and the troposphere is warming, that, yeah, it gets cooler as you go up, but if everything down below is warming, you should see some warming up here as well. Eventually that hot air is going to rise, right?
Absolutely.
So this is a major concern. This is something crazy. Wait, why does one data set looking at oxygen excitation tell us it's blue, and then the other data set right below it is telling us it's red? We'll go over this a lot more when we get into later chapters and we get into atmospheric composition. But what if I were to tell you that CO2 rises only as high as the troposphere and doesn't go into the stratosphere? And remember, the CO2 is going to be the thing we're going to learn later on that blocks the heat from getting out, right? So if it blocks the heat, it's like a ceiling on our world where the heat's trapped below in our greenhouse and it's not getting up into the stratosphere. And so we'll see later on when we talk about atmospheric composition that many of the global warming models actually predict that the stratosphere should cool while the troposphere heats up, because more of the energy that should be going all the way out into space is being trapped below. And the more CO2 that we get, the less energy is going out into space. It's got to pass through the stratosphere to get there, but it never gets through the stratosphere. So the stratosphere starts to cool down. So this in actuality is going to match our predictions later on when we talk about this stuff. But right now we're just trying to become acquainted with satellite data. Okay. So here's microwaves sounding satellite data combined with other satellite data, and these are two different satellites. This is showing you from about 1970 all the way to 2010 in this particular graph. Seems to suggest kind of a trend. One of the things, though, that I want to point out when we're talking about the atmosphere, and this is, I think, really, really important to understand when we talk about the amount of carbon we're shoveling into our atmosphere, greenhouse gases, is that our atmosphere doesn't actually go very far. So here's a picture of where we live. This is the surface of the Earth, okay? That can be shown by this little line here. Here's Mount Everest. Here's the Mariana Trench. So we live in this little tiny thin layer. Okay, here's our clouds. Here, this is our troposphere. The stratosphere is around here. Mesosphere and thermosphere. Okay, and just to put a fine point on it, here's a picture from space. Our astronauts took a nice picture of the Earth. Look at the atmosphere here. Here's the Earth. Look how thin that atmosphere is. Okay, beautiful picture, by the way, but that's not very thick. You don't get a sense of it when you look up in the sky, right? So it's incredibly humbling to realize just what tiny of a percentage of the planet we actually inhabit. So here's the Earth. The red stuff here is the lava, the mostly molten core of the Earth. We live on this thin surface, and then there's this thin band that comprises the troposphere, the stratosphere, the mesosphere, and the exosphere. Here's another pretty picture to give you kind of an appreciation of that. And the last thing I'd say on that is if the Earth was a marble, the atmosphere would be the thickness of the polish that they put on the marble. Okay? It may go up a few hundred kilometers if you're talking about the exosphere, but it's relative to the size of the Earth and the radius of the Earth or diameter of the Earth is much, much, much smaller, right? Okay. So here's a comparison of the satellite record and the surface thermometer temperature record. The satellite record is shown in blue. The surface record is shown in orange. And then this is an overlay of the two. And we're only looking from 1970 to 2023, because remember, we didn't have satellites up tracking temperature way back, before the 1970s. Okay, so one of the limitations of the satellite record is that it's much shorter time span. Okay, now when we had talked last time about logical fallacies and how they can be used to misrepresent climate change and even say that the Earth is cooling, the example that the little video I had showed you of Senator Ted Cruz had chosen time points in the satellite record. He had chosen 1999, and then he was speaking at around here, 2015. And so he was looking at this difference saying, indeed, there's no warming. In fact, it looks like it's cooled a little bit, right? So remember, it's only meaningful, even with satellite data, to talk about long-term trends. You have to look over a long period of time. Now, what do you think about the comparison between the satellite and the surface records? Do you see agreement? Do you see difference? What do you think? Do they track well?
I personally see agreement, though the satellite one has quite a market variability compared to the surface temperature.
Mm-hmm. Mm-hmm. There seem to be higher upswings. Now, the higher upswings do seem to correspond to upswings in the surface temperature, but their magnitudes seem to be much greater, right? Same thing with these downswings. So there does seem to be a lot more variability in the satellite records as compared to the surface records. That's something each to note. Do they have the same trend? Yeah. So I see a lot of head shaking, yes. So yeah, we're looking at a strong trend upwards. Okay. So as we were saying with their satellite record, it's a relatively short time period. It's only available from like 1980 on. It's an independent data set, so it has different kinds of errors that you get from the thermometer record. It measures it through different modalities, the infrared and microwave. It has its own errors, but those errors are not the same kinds of errors that you would get with the thermometer record. And when you plot both of these records together, you're going to see the trends are very similar. Okay. So the next thing I want to look at is, oh wait, let's see. Hold on a second. I think it's frozen here. Is about the ice record. So now we're going to look at a different data set. And it's important to understand, and please read the chapter on this. This is chapter 2, because they talk about the different kinds of ice. Not going to go a lot into it, but there's first year ice, there's second year ice, there's multi-year ice. The first year ice will freeze and thaw within a year. Okay. Second year ice, you know, it's ice that may have frozen a year ago or 2 years ago and may or may not be thawing now. And then below all that is the multi-year ice, stuff that stayed frozen for many, many years. Okay. It's also important to note the difference between ice that's on land versus floating ice. Okay. So ice that's on land, when it melts, if it melts, is going to leak into the ocean, and we would expect the ocean to rise. If you're talking about floating ice like icebergs, when they melt, they don't change the level of the water at all. If you don't believe that, the easiest thing to do is take a glass of water, put some ice in it, mark the level, you know, and have enough ice in it that the ice is floating. Not so much that it's all the way like pushing at the bottom, but that it's floating on the top. And then as that ice melts, you'll note that the water level doesn't change because ice is less dense than water. The water molecules, in order to satisfy all 4 of the possible hydrogen bonds that they could make with each other, have to move out to form this lattice. And since the atoms are further apart, that means it's less dense, so it floats. But some of it's submerged. The amount that's above the water is equivalent to the weight at which is being displaced from below. And so as it melts, the sea level doesn't change. Now, again, the ice record is going to be independent data set, completely different way of measuring this, would be completely different errors associated with those. But this is one of those things that's an indirect measurement of warming, right? Because we're not measuring a thermometer, it's not a temperature. But we would expect that if the temperature increases beyond freezing, that ice would melt. And so what do we see? So here's measurements of Antarctic ice. And this is seeing, so now we're looking at Antarctic ice. Sorry. And so what we're seeing here is, from 2004 to 2023, these are our Antarctic ice level measurements. And what we're seeing is a significant decrease in the total gigatons of ice. Okay, a lot of this is measured from satellites orbiting the Earth, taking pictures. We can calculate the amount of mass that's disappearing. And so we're seeing an average rate of change about minus 147 billion metric tons per year. So that's gigatons. So 147 gigatons per year since 2002. And what I've got here is a little video. Let me see if I can play it real quick. Go. One second, let me pull this little. This is courtesy of NASA. So this is showing, here's the date. And then you can see it's highlighting in colors, ice mass change. Here's where we are in the graph. You can see which areas are melting. Now this is the Antarctic. Now the Antarctic is in the southern hemisphere. So if it's warming, we might expect melting. Would we expect more melting in the southern hemisphere or the northern hemisphere? You're on mute.
The northern hemisphere.
So we would expect that while we're seeing 147 gigatons per year in the southern hemisphere in Antarctica, now the question becomes, what happens in the northern hemisphere? So one of the biggest ice masses is in Greenland. So we're going to go ahead and look at Greenland here. And this is the graph for Greenland. This has a rate of change of 271 gigatons per year of loss in sea ice. And so I'm going to bring that little video over here to show. Here we are on our graph. You can take a look at what it looked like before and see how it's changing. This is the areas that are getting are highlighted are the ones that are experiencing the most amount of change. And we're not even in 2020 yet. This is 2015. Now we're in 2018, 2019, 2020. There's COVID. And now we're getting closer to 2023. So you can see, as we might expect, in the northern hemisphere, more melting than we are in the southern hemisphere. So what we're doing with our data sets is we're slowly checking each one out. Do they match what we
lecture will be about 40 minutes.
Oh.
And after that, I will give anyone the opportunity to ask me questions for about 15 or 20 minutes. So the whole thing.
So we're looking at these data sets, comparing them to what our predictions might be. Here's for Arctic sea ice. We can see that's dropping as well. And it looks like before we get to bulk ocean temperature, we'll probably have to stop because it looks like we've reached our time point. So what are you guys' thoughts? First off, are you enjoying the class? Do you like what we're talking about? Are you learning anything?
Absolutely. I am enjoying, actually. I don't believe, I am enjoying the class, and it's eye-opening things that I have been questioning, and I finally get to get the answer right now. Thank you so much.
Now, it's important to remember the numbers that we're talking about. The 1.1 degree Celsius temperature anomaly, that's a global average, okay? Also in the previous lecture, we talked about the uneven distribution of that, how in parts of the northern hemisphere actually see a 3 degree centigrade anomaly up to 2023 as compared to the late 19th century. It's important to know those numbers. The amount of sea ice change, the amount of warming that we're seeing in the troposphere versus the stratosphere and the cooling in the stratosphere based on the satellite record, because you're going to want to be able to take all these different things together to make a really strong case while you know for sure not only is the climate warming, but by how much has it warmed right now? What are those numbers? What are the actual effects that we're seeing? And we'll talk more about that next time. So we've got still talk about bulk ocean temperature and sea level rise. And then we'll start looking at the ancient Earth and paleo proxies to see how much temperature has varied in the past. To find out, is this warming exceptional at all? Maybe it's just normal, as some folks like to argue.
Hello, Mr. Nicholas.
Glad to have you, class. So we have a new member that's just joining into class. You want to turn on your cam and introduce yourself real quick?
Yes, my name is Zakeo, and it was my first class. I lost the previous one because I was facing some issues, but now I'm ready to be a part. So thank you for the class. I really enjoyed it. So now I'm worried about the previous one because I think this is our third or our 40 class, and I'm worried because the previous one. I want to completely to be the same level with my colleagues.
So you got my email that's got all those links to the previous lecture videos. So you'll want to catch up and make sure you watch all of those. There's a link so you can introduce yourself on Flip. And then just follow along with that. If you've got any questions, just reach out. We can do our own independent Zoom so I can get you up to speed with everybody else. But welcome to the class. Glad you were here.
Really, really thanks. So, Mister, I tried to do it, but the problem I still don't have the Claflin email.
Right, which is why I'm going to be emailing you everything until you get those things.
It's okay. Thanks.
But with the flips, you can use whatever email you currently have. You don't need to use a Claflin email.
Okay, thanks.
Okay, thanks a lot, everybody. Have a great day, and I will see you on Friday.
Thank you, Prof.
Okay. Stay safe. Bye-bye.
Bye.